Yes? You're turning off here? Okay. Okay, so this will be kind of the overview of our next 45 minutes. This whole part is kind of like setting up context for structured streams. And then like the last 20 seconds, we'll talk about structured streams. If you if you're new to Spark, this is kind of what we talk about usually when we talk about Spark. The pipe is called Spark Core. And then on top of Spark Core, there is structured data, and graph computation. So these four are kind of like additional libraries that are built on top, and you don't have to use them, but most projects you'll find you use at least one or two of the additional libraries. The main idea for Spark, the main thing that makes it work is what's called an RDD, a resilient distributed data set. And if we read like the back of the box, it says, a parallelized, lazily evaluated, directed acyclic graph computation. So this says a lot, right? To build your model of what an RDD is, you can start thinking that it's a distributed collection, right? It's just an array or a list that works over a very large cluster. And we can talk a little bit about what each of these things mean. So it's not just a distributed collection, right? There's a few things that make RDDs really special. So one is when you are dealing with an RDD and you do any sort of transformation, let's say you have a very large collection of words and you want to get the uppercase version of all the words, you do a map, right, which transforms the content. But that doesn't actually transform the content right away. It gives you a second RDD that knows the transformation that's going to happen. So what happens as you're working with your data, you're slowly creating new RDDs, and you're creating this concept of lineage. Lineage is essentially each RDD that you create remembers where it came from. So when you have this cluster of 1,000 computers, 10,000 computers, and one of them goes down, when it starts back up, it'll remember how to rebuild itself because of this feature called lineage. So that's kind of the resiliency aspect of it, or one portion of the resiliency aspect. And then we have lazily evaluated, right? So in RDDs, we have concept transformations and actions. So I said when you get the uppercase version of all your words, nothing actually happens yet. You just get an RDD back. And the RDDs, so you create a whole lineage of RDDs, and they don't evaluate until you call an action. So this basically lets you manage when work gets done on your cluster. So it's kind of like a super brief overview. There's a lot more to RDDs, but for everything we're going to talk about, just remember that you have this very robust API that's backing all the operations that you do when you work with Spark. In the big data world, word count is the hello world, right? So it's the first app you write is the word count. So to think about the problem is, here we're counting on Shakespeare, and that's fairly small data set. I think it's like 2 megabytes. So it's fairly easy to count all the words that Shakespeare uses. But if you're counting a very large corpus, like all the tweets that Trump has ever tweeted about himself, you might blow up your computer. Like there's just not enough memory on your computer to count all those words. So that's why it's usually a big data problem. So big data problems is you just have such a big body of text that you're going to need several computers to work on it at the same time. Who here is familiar with Scala? Okay, like 5. So Spark is written in Scala. So that's kind of one of my examples in Scala. And it's also like a really fun language. I suggest you give it a try. So in Scala, this is kind of what a naive word count would look like. I say naive because we're splitting on space, so you can have like commas, periods. But I'm essentially saying I have a word, let's split on space, and I want to group all the identical words together, right? So tremendous gets put into a key, and then all the times tremendous appears is the value to my key value graph. And then I'm just counting value. So in Spark, it's pretty much the same. Like we have 2 lowercase, we have map, we have group by, we have map values. So the RDD API is very similar to Scala. And if you haven't used Spark before, this is kind of how you enter the Spark world. You create a Spark context, and then you just say Spark context, give me an RDD from this text file. So Spark also provides you with a visualization tool to see the transformations and the actions you're doing and when things are getting triggered. And this lets you kind of manage things like group by, cause severe shuffling of data. So this lets you visualize and manage how you're treating and working with your data. So this is the same as we just saw here. There's a flat map of group by and a map value. And so the visualization tool lets you see that in this way. So that was just a very brief overview of the core Spark library. Next, we're going to talk about the streaming library. So the streaming library is to solve any big data problems of an infinitely unending stream of data. So if you are interested in all the Facebook newsfeed, right? That's an infinite stream of data that's coming in. Twitter is an infinite stream of data that's coming in. So the Spark streaming library is to deal with this. And it's not pure streaming, it's in micro batches. So the idea is that you take a pure stream of data and you put it through Spark and you deal with that data in a micro batch. And micro batches have the smallest interval, half a second, right? So you get a half second worth of data, you transform it in some way, and you dump it somewhere. The way it works is that we use what's called a D-stream API, and so it's a discretized stream. So the discretized stream basically gives you an RDD at every interval. So in this diagram, the green is an RDD. So let's say every second, it pumps out an RDD, a discrete RDD. And then you have the concept of a window operation, right? So you can imagine that this is our window, and this is another window. To think about windows, Twitter is a really good example. On Twitter, you have the trending hashtags of every hour, right? So if you can imagine your window is that hour of trending hashtags, and it slides. So here it's sliding by 2 intervals. So you can say, you can imagine that our trending hashtags are not updating in real time, because that would be a lot of computation. So they probably update, let's say, every minute. So we have a window of an hour and a slide of 1 minute. And when you have that slide, that window produces another D stream. So we talk about this because it's complicated, and we don't really want to think about this sort of thing when we just want to write some ETL code, right? So this is the code, and it kind of looks the same as previously. We have a map, we have a split, and except instead of grouping my words, I'm grouping them within a window. So here it's like every 30 seconds, every 10 seconds, I want the word count of the last 30 seconds. So it's a slightly different idea. And then I have SSC here, and that's the Spark streaming context. So earlier we had a Spark context, and for streaming we have a Spark streaming context. So the next library we're interested in to think about structured streams is the SQL library. So the library is called SQL, and there's a collection in that library called DataFrames. So it's the API for computing structured data. And when we talk about structured data, we mean things like CSV, JSON files, databases, so anything that can be represented kind of like in a row and column format. So this is, again, two more examples of word count. So here's the DataFrame API version and the SQL version. This is a bit of a cheat, but there's an SQL context in like anything before Spark 2.0. So to get to the data frames, there's essentially a third context you have to initialize. So this is very similar, right? So you read a text file, you transform it into a data frame with a column called lines, and then instead of saying, earlier we had map, here we said it's select, but we still have a group by function here. So it's a little different because we're dealing with strings now, whereas earlier we kind of knew what we were dealing with, right? So here we're just saying there's a column called words, and we're hoping that there really is a column called words, and whatever it is inside, we can count it. And here we're hoping that there's a column called lines, and that we can actually split that column called lines. So that's one way to deal with our data frames. And the next way is to write straight up SQL. So this is SQL code. It's word count in SQL. It took me like a month to write. So there's a SQL DSL essentially that just lets you write almost any SQL you can think of, and that'll run against the data frames that exist. So here when we say line df, there's actually a data frame called line df, and then we're hoping that there's a column called line, right? We create a column called word.
When do you use data frame versus SQL? Is that depends on the source?
It depends on well, it depends on you, I guess. Some people are more familiar with writing SQL, so they like writing SQL. Like if you're a database developer, this always makes more sense to me. Just because you can do like stepwise functions, right? You can just like do one small transformation to another. Here you kind of have to reason the whole SQL out.
When the data comes in, like Twitter feed or Facebook feed, you are saying it could be like a data frame. How do you convert that? Is that after the conversion you are using that as a data frame?
So, well, I think you're about 10 slides ahead of me with streaming this. Okay, so the SQL library gives you these two DSLs, which is pretty cool. This one? Yeah. Maybe later. Okay, maybe later. So data frames are cool, but there's a lot more to them than just two DSLs, right? So you think about every other database you've ever used, there's some sort of query optimizer underneath it. And to give like a really simple example, imagine you have a student table and a classes table, right? And you just want to know who's taking CS 101. So if we did this like really naively, we'd say select students, select classes, join student to class, and then give me the student name and the class code. But this is maybe not the best way, because if you have a huge table, you're joining them both in memory, right? If you did it like the RDD way, you load two huge tables in memory and then you do this query on them. And joins are very expensive because you're moving data around just to make sure that the right student is on the same computer as the right class. So when you write SQL, that code gets optimized. And so the same thing happens when you write DataFrame and Spark SQL code. And the optimizer is called Catalyst. So Catalyst does three things. It does analysis. So analysis basically just goes through your code here and here and make sure that, hey, you do have a data frame called line, you do have columns called word and line. Right? It just goes in and it substitutes all the unknown values with references to real data. And then there is a logical optimizer. And a logical optimizer takes care of kind of the rules we just talked about. If you're doing a join and then a filter, it'll try to do a filter first before it does the join. It'll try to get rid of all the columns you don't need as soon as it can. It has like binary comparisons instead of looking up true or false. Right? So there's about 100 independent rules that it applies at the logical optimization stage. Then there's the physical planner. The physical planner has about 30 rules, and it cares about where data is. So it's literally physical, like where on each machine should the data be to execute this query in the best way possible. So it generally generates several physical plans, right? Because it's non-deterministic. And then it chooses the best plan, and then generates the code to execute that.
Does it really know where the data is, or does it really guess about it?
It knows where the data will be. Yeah, it's pre-processing. Okay, so that's Catalyst. What's also cool about Catalyst is that you can write your own rules. You can write your own rules for each of the three planners. So if your domain somehow makes more sense to do something else, or if you want to really control how data is split, you can write like physical planning rules.
Does that mean specific to the Apache?
Catalyst? Yeah. Catalyst is the query planner. So on top of Catalyst, we have Tungsten. So if you think about 2008 is when Spark just started, right? There was another big election that year. But if you think about computers were 3 gigahertz processors, I think like probably 4 gigs of RAM. We had disk-based hard drives. We had like 10 gigabit internet speeds. And now, 8 years later, the computing world looks really different, right? I have 16 gigs of RAM on this guy. I have an SSD. AWS internet speeds are like 100 gigabit. But our processors are still kind of 3 gigahertz. They haven't really passed that threshold. So Tungsten is an acknowledgement that processors are now the limiting agent in a lot of big data processes. So there isn't like a Tungsten optimizer. It's an overall project for small, low-level optimizations inside Spark. So I'll go through a couple of examples. So memory management and binary processing. So if you think about, so Spark is on the JVM, right? It runs on the JVM. If you think about a JVM object, it has a lot of overhead. Like a 4-byte number isn't stored in 4 bytes on the JVM. It's like 50 bytes. And that's not insignificant if you're dealing with billions of numbers. So there's, so for like primitives like that, Spark tries to deal with them at a binary level. So there's a library called sun.misc.unsafe that lets you essentially escape the JVM. So things like numbers get stored in binary as binary data without the overhead. So if you have a billion numbers, you save 40 bytes times a billion. But what's also really cool is that to serialize between machines, we're now only serializing 4 bytes instead of 50 bytes. And that makes a really big difference. And Spark it essentially generates its own serializers whenever it has to deal with binary data that it manages. And on top of that, we have Catalyst that tells us exactly when and where we need data. So Spark can use that information to manage its memory very, very explicitly. The third broad category of optimization is cache order computation. So I'll give you just one other example, and that's sorting key value pairs. So the traditional way to sort key value pairs is that in your CPU cache, you have an array of pointers to key values in memory, right? And just as waiting for data to get into memory from disk is slow, for the cache to wait for memory is sometimes slow. So in some instances, waiting for RAM is really what's slowing down some processes. So for things like sorting key value pairs, Spark will store the keys in cache in something called a binary map, right? So in Java, you have like a hash map, but Spark has a binary equivalent called a binary map that will store some information in cache. So it can sort the keys in cache instead of having to wait to dereference the pointer to RAM.
Are you talking about the hardware level 2 cache?
Yeah, like L1 and L2.
Right. Yeah. Question, map R, right? Map R is not in Java, in C++.
Say that again.
Map R.
Map.
M-A-P-R.
Yeah.
Derived in C++. Not in Java.
Map.
What are distribution of the Spark? Map R.
So map R is a distribution of Spark, you're saying, yes. And it's written
in C++.
I don't know. Maybe.
How do they do this in C++?
Like they've rewritten Spark in C++?
Something like this.
Oh, okay.
The reason why they faster Java is...
So maybe it's just a Java optimization. Okay. Generally, when they talk about Tungsten, they compare it to C++ code. Like in best case, it's like 90% as fast as C++. So this is probably not the same as well.
Java besides they're 60 times faster than Java.
Okay.
Because they're C++.
Yeah. So maybe take this like the scale with a grain of salt, but in general, DataFrames are much faster than RDDs. And if you're coming from the Python world using RDDs, you're kind of screwed, right? But in the DataFrame world, all 4 supported languages have the same performance. Okay, so finally, now that we have all this context, we can talk about structured streams. So Spark 2.0 is the alpha release of structured stream. So if you guys have followed Spark development, every time they do a new library, they really just introduce the thinnest thread of functionality, just kind of like, hey, this is what we're thinking of doing. And it's just an A through Z, will get you from point A to B with not production-ready code, right? So the original streaming library was like that, data sets, DataFrames was like that. It's just introduction of concepts and basic API. So if you download Spark today, that's really the structured stream library is very thin, but it can get you from A to Z and get you familiar with the ideas behind it. So what they're selling it as is fast, scalable, fault-tolerant, end-to-end, exactly once, stream processing, without the user having to reason about streaming. So we'll talk about what all of this means in the next 10 seconds.
Meaning easier than history.
Yes, yes.
What they say about Splint? They faster than Splint?
Then Flink?
Splint.
Splint.
Not Splint, another system is Splint. Apache Splint.
Oh. I don't think they're saying it's faster. I think they're saying it's a unified API to do a lot of things without thinking about streaming. So this is your traditional streaming, right? When people first thought about streaming, this was kind of the idea. We have some data that comes in, we're going to do something with it, we're going to like transform it somehow, we're just going to dump it in a database or something, and then somebody else will pick up the baton and display it to the user or whatever. But I'm sure most of you guys have worked with applications that aren't that simple when it comes to streaming. So what a lot of people do with streaming now is, right, you get this huge influx of data from Kafka. You do some sort of transformation, and you still send it to the database. But then you do things like, oh, I want to hook a notebook, like one of those Python notebooks to this data and query it and see what's happening in real time. I want like dashboards to report to me what's going on. And I want a machine learning model that I don't have to update nightly, over like a 10-hour-long process, but I want it to update as data is coming in. So this is certainly very possible today still, but you have to build a lot of scaffolding and plug in a lot of libraries that maybe weren't meant to work together very easily. So the idea behind structured streams is that all of this can be encompassed in one library, structured streams. So the idea is a simple one. The idea is just to treat our stream as a table that's growing infinitely. And as new data is coming in from the stream, we just treat it as new rows that are being added to our table. So this is kind of what conceptually word count would look like, right? Here I have an incoming stream from my console, and I'm treating all these incoming streams as a growing table. I do my word count, and I have what we call a result table here. But this result table is just constantly updating with new counts. So maybe this is not very helpful, so we have accompanying code. So before we saw, like, there's a Spark context, there was a streaming context, there was an SQL context, and up until Spark 2.0 that was the case, and now we just have a Spark session object. So the Spark session object will now encompass all those three contexts. Right, so this is my Spark session, and I say, read this directory as a stream, do my data frame operation to do a word count, and then write it to the console. So it's very simple, and a lot is happening underneath the surface. So for example, if I took out, this would become a batch job. This code would be, I wouldn't have to change this code at all. It would run whether it's a stream or not. So I don't have to think about intervals. If I wanted to have like a window operation, I wouldn't have to like care that my batch and my interval aren't multiples of each other, right? There's no like confusion between a DStream API and an RDD API. This is just straight up DataFrames.
What's the output mode?
So there's 3 output modes. There's complete, where it dumps the whole result table every time. There's new and update. So new is only new rows, and update is rows that have been updated.
I saw it. I think
Or maybe append, yeah. Append new.
that should be reduced by make it faster. Because,
Instead of group by?
yeah.
It's just an example.
Well, yes, but well, streaming is not different. Because, if you use group by, it's true that it doesn't save the result into the memory instead of just save the result in group by. So basically, as the stream goes longer and longer, the old result
Actually, it doesn't matter because for the catalyst optimization, you actually change it to
yes.
And
the framework will do it for you. So if you were using the old one, then it actually matters. They are actually not to use full line.
Yeah.
But then now with Spark 2.0, with the new framework and catalyst optimizer, you actually behind the scenes change to within Spark T, which is more efficient. So yeah, you're right. But the framework actually take care of it, so it doesn't matter, right?
And so one other thing to notice is that well, these two are growing infinitely at the moment. There's no mechanism to shorten them yet. So he's right. They're just growing infinitely at the moment, and it's basically because it's alpha code, right? It's just to get used to the idea of what's happening. So we mentioned structured streams have end-to-end exactly one guarantees. So what this is a delivery semantic, right? So if you think about text messages, I was on Win Mobile for a while. It was like a really bad relationship, but I kept staying on it. But with Win Mobile, like I'd go in my basement, I'd come back upstairs, and I'd get the same text message like delivered to me 3 times, right? Does that happen to everybody else? Like sometimes you don't get text messages. Sometimes you get the same text message multiple times. Not because somebody's needy, but because carriers haven't really solved end-to-end exactly once semantics either. It's a hard problem. It's a hard problem to say, if I send a message out to somebody, I want them to get it, and I only want them to get it once. So there's akka, if you're familiar with akka. Akka has at most once guarantees, right? So like, you might get the message, you might not, but you won't get it twice. So like, people have implemented at most once guarantees pretty easily. They've implemented at least once guarantees pretty easily, but exactly once is a fairly tough problem. So there's some structure in structured streaming to help us with exactly once guarantees. So we'll look at this picture to kind of explain it. So you remember Catalyst? Catalyst is our planner. So every time new data comes in, Catalyst will make a plan for that new data. So that's different from what you were asking about, because it's in the old RDD framework, once you switch to, like, you have a D string, you say to df, then Catalyst has to make a whole new plan. So here, Catalyst just makes a plan for new data, as opposed to like recalculating the entire query. So Catalyst will make what's called an incremental plan just for the new set of data that's come in. And then it stores that plan in a write-ahead log. So it writes this plan into an HDFS file before it does anything with it. So then if it's executing after it's written this file, after it's written this plan, it can always go retrieve that plan later and re-execute the plan that it didn't finish. So in between executions, we store state. So we're storing the top tweets of the hour. And if our cluster fails, we come back, we have our plan, and we want to update the top tweets of the hour. We have to keep that safe in some way. So it's kept in essentially HDFS files. There's an API that stores state creatively called the state store API. So right now there's only one implementation. It's Delta files in HDFS. So we have a plan. We're executing, and if we fail during execution, we can go back to our plan, go back to the state. So that leaves us with our source and our sink, right? So I got my plan back. I failed. I got my plan back. How do I get the data that I was calculating? So I have to go back to source. So the source API in Spark 2.0 is very different and very restricted. If you implement a source, you have to implement replayability. So you think of Kafka, right? It's you're scrolling through a journal. You have to be able to go back and scroll forward again. So that's replayability. And so you'll probably find that structured streams probably won't have the same number of sources as the dstream API because of this restriction. And then we have sinks, right? So with a sink, if I finish my calculation, I wrote half of it down, the cluster fails, I have another half to write. But when I come back, I get my data, I get my plan, I get my state, and I start writing again. How do I stop myself from writing that first half of the data? Right, at most once guarantee. So the restriction on sinks is that they have to be idempotent now. So idempotent means one thing in math. In streaming, it means every time you get a message, you have to be able to produce the same result.
Meaning the sink has to be able to go into
duplicates. Yeah, exactly. So essentially, APIs have kind of pushed the responsibility to the sources and the sinks.
So the one thing that you have here, I can say about the sync, but it's quite another thing that you say, for example, my process failed at like 70%. Then if I were to actually come back and start from 0 and come back to 70%, yeah, it doesn't matter because of the idea of coaching sort of property of the sync. But then I'm reaching 70% of the time. I want to start right at 70 and go back to finish the other 30. So how does it do that? Does it do that?
No, it doesn't actually do that. Again, it's alpha code. So right now it wouldn't re-execute the whole thing. The only, you could tune, your intervals essentially. You could tune your intervals to do more work in smaller amounts of time. But right now, no, there's no way to resume from exactly where you left off, except for the batch.
Can you talk a little bit about the data solve API in terms of the ability to push down some of the, say, if you do a select statement, that it actually can pull down that to data solve so that you actually see the data using the data solve. So that you won't actually have to supplement data.
So the data source API isn't public yet. So they haven't even released the public API for data sources. It's something that's coming in 2.1, I think. Okay. Is it?
Yeah.
Okay, I haven't looked at it. So the data source API, they said it would be in 2.1, but you can imagine, I think Kafka was the first on their hit list of this makes the most sense So that's it. Structured streams gives you, lets you write SQL for streaming code. That's pretty cool. Lets you use DataFrames. It gives you query optimizer, the low-level JVM optimizations. It's the same code for batch and streaming. There's some differences. You can't like join two streams, right? But you can join two data frames. But things like streams, you can't join them. So there's a small subset of operations you can't do. If you're like really excited, some DBAs can now do streaming because it's just the same library. You have exactly one's guarantees that you don't have to give too much thought to. No need to think about intervals. Intervals are so painful, guys. If you use T streams, they're not easy. And I didn't really talk about it, but event time primitives. So there's two times in a stream, right? There's delivery time when you got the message and event time when the message actually happened. Event time is now really easy to deal with. There's basically just a column that says event time, so you group by event time.
Apparently it's a fairly hard problem to get it running.
Yeah. There's a video from Spark Summit where they do like an event time demo, and you can see when they essentially do a group by event time, and old columns get updated in a group by. Yeah, old rows get updated in a group by. So in the future, again, we're talking basically just a very basic alpha API now. In the future, there's Kafka should be in 2.1. The public API for sources and sinks will be released. Watermarks. Remember when I said those two infinitely growing tables are currently infinitely growing? Watermarks is the way to deprecate old data. And ML integration. Right now, I think K-means is the only ML model that lets you update as data is coming in. So the idea is that all the other ML models will eventually support a streaming update. So if you want to follow me on Twitter or GitHub, it's long Tran with 5 O's. And the success of every talk is measured by new Twitter followers. And the slides on GitHub, and if you're really curious, there's like a very long list of videos and blog posts with which I used to build this talk.
Did anyone mention that 2.1 was actually released?
Yeah, he said it was released. I haven't heard it. But... so that's it. Thank you.